Hi, we are from AS12 Group 7. Our lecturer is Sumama Rabani Afar. Today we are going to presenting about experiment 6, which is high performance liquid chromatography HPLC. Here are our group members. The first one are Muhammad Farid Shami. The second one is Nur Afika. The third one is Nur Shahira, and the last one is me, Zadia Adli Malkis. To start with, I'm going to give some introduction about HPLC. HPLC is utilize a liquid mobile phase to separate mixture component. It is then the analytes are dissolved in a solvent while forced through a column under high pressure. HPLC is versatile and will separate a wide variety of chemical mixture, including a non-volatile as well as a thermally unstable compound. Next, we are going through the objectives. In this experiment, there are 3 objectives. The first one is to determine the retention time of a standard solution. In this experiment, we use caffeine as the standard solution. The second objective is to identify the caffeine peak in a soft drink sample. And the third objective, which is the last one, is to determine the amount of caffeine in a soft drink sample using the response factor method.
Next, I will explain about the methodology for the HPLC experiment. The process begins with the solvent reservoir, which contains the mobile phase. This mobile phase is essential for transporting the sample through the system. The solvent flows from the reservoir into the pump. The pump draws the mobile phase from the reservoir and forces it through the system at high pressure. This high pressure ensures a steady and controlled flow of the mobile phase. The pump is connected to the injector. The injector introduces the sample into the mobile phase stream without disrupting the flow. It ensures the sample mixes uniformly with the mobile phase. The injector then directs the sample mobile phase mixture into the guide column. The guide column is a smaller column placed before the analytical column. It removes impurities and protects the main analytical column from damage. The purified flow then continues into the analytical column. The analytical column is the heart of the HPLC system. It contains the stationary phase that interact with the sample component. As the mixture flows through the column, the components separate based on their affinity to the stationary and mobile phase. The separated component exits the column and moves to the detector. The detector identifies and measures the separated component as they come out of the column. Different detectors like UV-Vis, fluorescent, and electrochemical detector are used depending on the sample. The signal generated by the detector is sent to the data system. The data system, usually a computer with a specialized software, collect the detector signal, process it, and display the result as a chromatogram. The chromatogram provides information on the retention time, concentration, and identity of each sample component.
This is the result of caffeine in caffeine standard, and the retention time is 2.48. Next is results of caffeine in Cook, and we choose the fourth peak, which is the retention time is 2.481. And lastly, the caffeine in Libita, and we choose third peak, which is the retention time 2.219. In caffeine standard compound, when the retention time is 2.482, the peak area of caffeine is 6,249.48779. In Cook compound, when the retention time is 2.481, the peak area of caffeine is 7,001.12305. The compound caffeine in Libita, when retention time is 2.219, the peak area of caffeine we get is 1.03421 times 10 power of 4. To calculate RF in caffeine standard, we choose peak area caffeine standard over concentration of caffeine. And based on the graph, the peak area of caffeine standard is 6,249.48779 over 1 milligram per milliliter, equal 6,249.48779 milligram per milliliter. To calculate concentration caffeine in Coke, peak area caffeine in sample over RF. Based on the graph, we choose 7,001.12305 over 1.00678 times 10 power of 4 milligram per milliliter, and we get 0.6954 milligram per milliliter. But we have to change the milligram per milliliter to ppm. So we calculate 0.6954 milligram per milliliter over 1 times 1000 ppm over 1 milligram per milliliter, and we get 6,095.4 ppm. Concentration caffeine in data equal peak area caffeine in sample over RF. Based on the graph, we choose 1.03421 times 10 power of 4 over 1.00678 times 10 power of 4 milligram per milliliter, and we get 1.0272 milligram per milliliter. To change milligram per milliliter to ppm, we calculate 1.0272 milligram per milliliter over 1 times 1000 ppm over 1, and we get 1027.2 ppm.
In conclusion, by using high precision liquid chromatography, we get to achieve all of our objectives. By using Hplc, we get to determine the retention time of a standard solution. We also get to identify the caffeine peak in a soft drink sample. And lastly, we also get to determine the amount of caffeine in a soft drink sample using the response factor method. Hplc is a precise and versatile analytical tool, allowing us to analyze complex mixture with exceptional accuracy. It is primarily used for separating, identifying, and quantifying compounds, making it an essential technique in many industries. Hplc has widespread applications such as including pharmaceuticals, food testing, environmental analysis, and biotechnology, demonstrating its importance across diverse fields. Its high sensitivity combined with the ability to customize operational parameters ensure that we can adapt it to specific analytical requirements. In summary, high-precision liquid chromatography remains a cornerstone of modern analytical science, indispensable for advancing research and ensuring quality in many areas of our lives. That's all from me. I hope this video has been very beneficial to you. Thank you.